The large language model families. Large language models, LLMs, mainly refer to transformer-based pre-trained language models, PLMs, that contain tens to hundreds of billions of parameters. Compared to the PLMs reviewed in another video, LLMs are not only much larger in model size, but also exhibit stronger language understanding and generation capabilities, along with emergent abilities that are not present in smaller-scale models. In what follows, we review three LLM families, GPT, Llama, and PaLM, as illustrated in this figure. The GPT family, Generative Pre-trained Transformers, GPT, are a family of decoder-only transformer-based language models developed by OpenAI. This family consists of GPT-1, GPT-2, GPT-3, InstructGPT, ChatGPT, GPT-4 Codex, and WebGPT. Although early GPT models, such as GPT-1 and GPT-2, are open source, recent models like GPT-3 and GPT-4 are closed source and can only be accessed via APIs. GPT-1 and GPT-2 models have been discussed in the early PLM subsection. GPT-3 is a pre-trained autoregressive language model with 175 billion parameters. It is widely considered the first LLM in that it not only is much larger than previous PLMs, but also for the first time demonstrates emergent abilities not observed in previous smaller PLMs. GPT-3 shows the emergent ability of in-context learning, meaning it can be applied to any downstream tasks without any gradient updates or fine-tuning, with tasks and few-shot demonstrations specified purely via text interaction with the model. GPT-3 achieved strong performance on many NLP tasks, including translation, question answering, and close tasks, as well as several requiring on-the-fly reasoning or domain adaptation, such as unscrambling words, using a novel word in a sentence, and three-digit arithmetic. Figure shown here plots the performance of GPT-3 as a function of the number of examples in in-context prompts. GPT-3 shows that larger models make increasingly efficient use of in-context information. It shows in-context learning performance on a simple task requiring the model to remove random symbols from a word, both with and without a natural language task description. Codex, released by OpenAI in March 2023, is a general-purpose programming model that can parse natural language and generate code in response. Codex is a descendant of GPT-3, fine-tuned for programming applications on code corpora collected from GitHub. Codex powers Microsoft's GitHub Copilot. WebGPT is another descendant of GPT-3, fine-tuned to answer open-ended questions using a text-based web browser, facilitating users to search and navigate the web. Specifically, WebGPT is trained in 3 steps. First, to learn to mimic human browsing behaviors using human demonstration data. Then, a reward function is learned to predict human preferences. And finally, WebGPT is refined to optimize the reward function via reinforcement learning and rejection sampling. To enable LLMs to follow expected human instructions, InstructGPT is proposed to align language models with user intent on a wide range of tasks by fine-tuning with human feedback. Starting with a set of labeler-written prompts and prompts submitted through the OpenAI API, a dataset of labeler demonstrations of the desired model behavior is collected. Then, GPT-3 is fine-tuned on this dataset. Additionally, a dataset of human-ranked model outputs is collected to further fine-tune the model using reinforcement learning from human feedback, RLHF, as shown in this figure. There are 3 major steps in RLHF. In the first step shown, goal is to collect demonstration data and train a supervised policy. This involves sampling a prompt from a prompt dataset. Then a labeler demonstrates the desired output behavior. After that, the data is used to fine-tune GPT-3 with supervised learning. For second step in the illustration, the goal is to collect comparison data and train a reward model. This begins with a prompt and several model outputs sampled. A labeler then ranks the output from best to worst. This data is then used to train our reward model. Finally, for the third step in the illustration, we aim to optimize a policy against the reward model using reinforcement learning. This starts with sampling a new prompt from the dataset, and the policy then generates an output. The reward model then calculates a reward for the output. This reward is then used to update the policy using Proximal Policy Optimization, PPO. As an aside, Proximal Policy Optimization is a reinforcement learning algorithm that optimizes decision-making policies directly. It improves training stability and efficiency by using a clipped objective function to limit the size of policy updates. PPO is favored for its simplicity and effectiveness across various tasks, including robotics and games. The resultant InstructGPT models have shown improvements in truthfulness and reductions in toxic output generation while having minimal performance regressions on public NLP datasets. The most important milestone of LLM development is the launch of ChatGPT on November 30, 2022. ChatGPT is a chatbot that enables users to steer a conversation to complete a wide range of tasks, such as question answering, information seeking, text summarization, and more. ChatGPT is powered by GPT 3.5 and later by GPT-4, a sibling model to InstructGPT, trained to follow an instruction in a prompt and provide a detailed response. GPT-4 is the latest and most powerful LLM in the GPT family. Launched in March 2023, GPT-4 is a multimodal LLM that can take image and text inputs and produce text outputs. While still less capable than humans in some of the most challenging real-world scenarios, GPT-4 exhibits human-level performance on various professional and academic benchmarks, including passing a simulated bar exam with a score around the top 10% of test takers, as shown in this figure, which illustrates GPT-4 performance on academic and professional exams compared with GPT 3.5. Like early GPT models, GPT-4 was first pre-trained to predict next tokens on large text corpora, and then fine-tuned with RLHF to align model behaviors with human desired outcomes. The Llama family. Llama is a collection of foundation language models released by Meta. Unlike GPT models, Llama models are open source. In other words, their weights are made available to the research community under a non-commercial license. This accessibility has led to the rapid growth of the Llama family, as many research groups utilize these models to develop better open-source LLMs to compete with closed-source versions or to create task-specific LLMs for critical applications. The initial set of Llama models was released in February 2023, with sizes ranging from 7 billion to 65 billion parameters. These models have been pre-trained on trillions of tokens sourced from publicly available datasets. Llama employs the transformer architecture similar to GPT-3, with minor modifications such as using a SWGLU activation function instead of ReLU, employing rotary positional embeddings rather than absolute positional embeddings, and utilizing root mean squared layer normalization instead of the standard layer normalization. The open-source Llama 13, which is a 13 billion parameter model, surpasses the proprietary GPT-3 175 billion parameter model in most benchmarks, establishing it as a solid baseline for LLM research. In July 2023, Meta, in collaboration with Microsoft, released the Llama 2 collection, which includes both foundational language models and chat models fine-tuned for dialogue, known as Llama 2 Chat. Llama 2, the next generation of Meta's large language model, is available under a permissive commercial license. This marks a shift from Llama 1, which was limited to non-commercial use, indicating that Llama 2 can be used for both research and commercial purposes. These Llama 2 chat models have demonstrated superior performance over other open-source models in many public benchmarks. Illustration in this figure shows the training process of Llama 2 Chat. The training process for Llama 2 Chat starts with pre-training on publicly available online data, followed by supervised fine-tuning to create an initial version. This version is then refined iteratively through RLHF, rejection sampling, and proximal policy optimization. During the RLHF stage, accumulating human feedback is crucial to fine-tune the reward model without significantly altering it, ensuring the stability of Llama model training. Alpaca, fine-tuned from the Llama 7B, a 7 billion parameter model, using 52,000 instruction-following demonstrations in the style of self-instruct with GPT 3.5, is notably cost-effective for training, especially for academic research. It performs comparably to GPT 3.5, despite being significantly smaller. The Vicuña team developed a 13 billion parameter chat model, Vicuña 13B, by fine-tuning Llama with user-shared conversations collected from ShareGPT. Preliminary evaluations with GPT-4 as an evaluator show that Vicuña 13B achieves more than 90% of the quality of OpenAI's ChatGPT and Google's Bard, outperforming other models like Llama and Stanford Alpaca in the majority of cases. This figure illustrates the relative response quality of Vicuña and a few other well-known models by GPT-4. Vicuña 13B also boasts relatively low computational demands for training, with costs around $300. The Guanaco models are fine-tuned llama models using instruction-following data, achieving efficient fine-tuning through QLoRa, which stands for Quantized Low-Rank Approximation. QLoRa enhances the efficiency of large language models by reducing the model size and computational requirements without significantly compromising performance by using lower bits and splitting apart matrices into more manageable sizes that are easier to process. This approach allows fine-tuning a 65 billion parameter model on a single 48 gigabyte GPU. The best-performing Guanaco model rivals all previously released models on the Vicuña benchmark, reaching 99.3% of ChatGPT's performance with just 24 hours of fine-tuning on a single GPU. Koala, another instruction-following language model built on Llama, focuses on interaction data, including user inputs and responses from advanced closed-source chat models like ChatGPT. The Koala 13B model, which has 13 billion parameters, is competitive with leading chat models based on human evaluations using real-world prompts. Mistral 7B, a 7 billion parameter model, is engineered for exceptional performance and efficiency, outperforming the best open-source 13 billion parameter model, such as the 13 billion parameter Llama 2 and the 34 billion parameter model, the Llama 34B, in reasoning, mathematics, and code generation. This model utilizes grouped query attention for faster inference and sliding window attention for handling sequences of arbitrary length more efficiently. The Llama family continues to expand, with more instruction-following models being developed, including Code Llama, Gorilla, Giraffe, Vagon, Tulu 65B, Long Llama, and Stable Beluga 2, among other models. The PaLM family, which stands for Pathways Language Model, is a series of groundbreaking language models developed by Google, has significantly advanced the capabilities of natural language processing since its inception. The inaugural PaLM model, introduced in April 2022, was shrouded in secrecy until March 2023, when its prowess was revealed to the world. Boasting an impressive 540 billion parameters, this transformer-based large language model, LLM, represents a leap forward in the field. Its pre-training regimen, conducted on a vast corpus of 780 billion tokens covering diverse linguistic tasks and scenarios, sets a new standard for language model training. Key to the success of PaLM is its training infrastructure. Employing the Pathways system, PaLM is pre-trained across 6,144 TPU-v4 chips, leveraging parallel processing for efficient model training. This architecture not only facilitates scalability, but also enables PaLM to achieve state-of-the-art few-shot learning results across a myriad of language understanding and generation benchmarks. PaLM 540B's performance surpasses that of fine-tuned models on complex reasoning tasks, and even rivals human performance on benchmarks like BigBench. Expanding the PaLM family, subsequent iterations include the UPaLM models, featuring parameter counts of 8 billion, 8B, 62 billion, 62B, and 540 billion, 540B respectively. These models undergo a meticulous training process, starting with pre-training on a vast text corpus using the PaLM approach. Following this initial phase, the models embark on unsupervised language learning with repeated refinement, UL2R, a continuous training method that enhances model performance by incorporating additional data while optimizing computational resources. A significant stride in the evolution of PaLM comes with the development of FLAN-PaLM, an instruction-following model through instruction tuning on 1,800 tasks. This illustration outlines a comprehensive fine-tuning strategy employed to advance the capabilities of a language model, specifically the FLAN-PaLM 540B, through extensive training on a variety of instructional data. The fine-tuning process involved an extensive collection of 473 datasets grouped into 146 task categories, which span a total of 1,836 distinct tasks. This wide-ranging data collection ensures the model's exposure to a multitude of scenarios and problem types, simulating a rich educational environment. To facilitate a deeper understanding of the model's training regimen, Let's delve into the specifics of the datasets and tasks involved, as depicted in the accompanying illustration. The fine-tuning tasks are categorized into different groups, each with its specialized focus. TOSF. This stands for Task-Oriented Semantic Forecasts. This is a fine-tuning aspect, leverages a broad array of 55 datasets across 14 distinct categories to enhance the model's skills in common-sense reasoning and question generation. It also includes adversarial question answering, which trains the model to respond to deliberately challenging or misleading questions, totaling 193 tasks. This category ensures that the model can navigate a range of conversational contexts and discern nuances in human language. Muffin. The Muffin category prioritizes comprehension and generation in a natural language context, involving 69 datasets across 27 categories with 80 tasks in total. It encompasses natural language inference, where the model deduces implicit meanings in text, and extends to code instruction generation, which is about translating natural language instructions into code. Dialogue context generation is another critical part, where the model learns to create responses within the flow of a conversation, thereby enhancing its interactional abilities. COAT stands for chain of thought. As a pivotal element in fine-tuning, chain of thought involves 9 datasets focused solely on improving the model's sequential reasoning. Through chain of thought prompts, the model learns to articulate step-by-step reasoning, mirroring a human-like problem-solving process. This enhances the transparency and traceability of the model's thought process in solving complex problems across 9 tasks. Natural Instructions V2. This extensive group is composed of 372 datasets spanning 108 categories and includes 1,554 tasks. It aims to expose the model to a comprehensive suite of instructions for tasks like cause-effect classification, where the model identifies relationships between actions and outcomes, and text categorization, where it organizes text into predefined categories. This category also trains the model to recognize and handle toxic language, ensuring it can maintain constructive and safe interactions. The Natural Instructions V2 collection serves as a substantial resource for teaching the model to execute a diverse range of commands and to understand the intent behind instructions, thereby amplifying its applicability and robustness in practical scenarios. The fine-tuning regimen is complemented by what's referred to as held-out tasks, which serve as benchmarks to assess the model's generalization and performance on tasks it has not explicitly trained on. First within the held-out tasks begins with MMLU. MMLU stands for Massive Multitask Language Understanding. This acronym refers to a benchmark designed to test the model's understanding across a variety of subjects and disciplines. MMLU includes a wide-ranging set of multiple-choice questions that challenge the model's knowledge in highly specialized areas such as abstract algebra, a branch of mathematics, college-level medicine, which pertains to medical knowledge typically taught in a university setting, and professional law, which includes legal principles and practices relevant to a professional lawyer's education. The MMLU consists of 57 tasks, each designed to measure the model's depth of understanding and its ability to apply knowledge to new situations. Next is BBH. BBH handles Boolean expressions, tracking of shuffled objects, and word sorting tasks. This set of tasks is engineered to probe the model's logical reasoning, memory, and language structure skills. The Boolean expressions component examines the model's ability to comprehend and evaluate logical statements that use operators such as and, or, and not. Tracking of shuffled objects tests the model's memory and attention as it follows objects that are moved around, a task that mimics the cognitive shell game. Word sorting challenges the model to understand and apply rules of lexical or semantic ordering. Together, these 27 tasks provide a comprehensive evaluation of the model's cognitive abilities in logic, memory retention, and language processing. And then we have TIDICE. TIDICE stands for Typologically Diverse Question Answering. It is designed to assess the model's performance in question answering over a set of typologically diverse languages. It involves information-seeking questions, where the model must understand a query and provide a specific answer based on provided or known information. TIDICE is multilingual, covering 8 different languages, which implies that the model is evaluated not only on its knowledge and reasoning skills, but also on its ability to process and understand multiple languages, some of which may have less NLP research compared to others, thereby testing the model's versatility in linguistic diversity. Next is MGSM, which stands for Math Grade School Math. MGSM presents a collection of grade school level math problems designed to test the model's numerical and mathematical reasoning abilities. These problems are provided in 10 different languages, indicating that the model's numerical understanding is not limited to the syntax of a single language, but can be applied across linguistic barriers. The tasks within MGSM range from basic arithmetic to more complex problems that may require understanding of shapes, measurements, or logical reasoning, reflecting the type of math problems encountered by students at the elementary level. By training and evaluating on these diverse and complex tasks, the model's fine-tuning process aims not just for breadth of knowledge across different domains, but also depth in understanding and problem-solving capabilities, enabling it to perform well on a broad spectrum of real-world applications. This diverse fine-tuning strategy, particularly the inclusion of chain-of-thought reasoning, has significantly enhanced the model's performance. The model has learned not just to give direct answers, but to elaborate on its reasoning process, mimicking a more human-like problem-solving approach. Consequently, the FLAN-PaLM 540B model achieved a 9.4% improvement in its capabilities when compared to its predecessor, PaLM 540B. This improvement emphasizes the effectiveness of instruction-focused fine-tuning, which tailors the model's learning process towards understanding and executing tasks based on explicit instructions, ultimately making it more adept at handling a wide array of complex real-world applications. Moreover, PaLM 2 emerges as a compute-efficient successor to its predecessor, boasting enhanced multilingual and reasoning capabilities. Trained using a mixture of objectives, PaLM 2 exhibits superior performance on downstream tasks across various model sizes while enabling faster and more efficient inference compared to PaLM. In a bid to cater to domain-specific needs, MedPaLM emerges as a specialized PaLM variant tailored for medical inquiries. Leveraging instruction prompt tuning, MedPaLM aligns itself with medical domains using minimal exemplars, delivering high-quality responses to healthcare queries. The subsequent iteration, MedPaLM 2, further improves performance through med-domain fine-tuning and ensemble prompting, achieving notable success on benchmarks such as the MedQA dataset, setting new standards in medical question answering. In conclusion, the PaLM family stands as a testament to the continuous evolution and innovation in language model development. From its inception with the pioneering PaLM model to specialized variants like MedPaLM, each iteration pushes the boundaries of natural language understanding, setting new benchmarks and driving progress in the field of artificial intelligence. We hope you enjoyed this overview of the 3 major large language model families from OpenAI, Meta, and Google. If you want to share your perspective on this subject, leave a comment down below. Click the like button as well as the notification bell to get your recent updates. See you in the next video.